Okay, so hey everyone, good afternoon. Today our speaker for the Fast Code seminar is Sam Westrick. Sam's a PhD student at Carnegie Mellon, advised by Umut Akar. And Sam's research focuses on developing provably efficient and practical implementation techniques for parallel programming languages. Sam's also the lead developer of the MPL compiler for Parallel ML, which is currently being used at Carnegie Mellon to teach parallel programming to over 500 students every year. And today, Sam's going to tell us about his research on disentanglement as a way to do provably efficient parallel functional programming. So I'll turn it over to you now, Sam.
Excellent. And I just wanted to check, are we recording this talk? I can't remember do we need to do that in Zoom?
Yeah, so we're recording it now. Yeah.
Excellent, okay.
Yeah.
Great. Well, great, so thanks Julian, and thank you all for coming today. So as Julian said, I'd like to talk about this research I've been doing on disentanglement. This is an exciting memory property in parallel programs, which we find is quite common and which we're exploiting now to do functional programming more efficiently. So there's a number of people involved in this project. My advisor, Umut Akar, you can see there, as well as Jatin is a student at CMU that we've been working with. Rohan is a former undergraduate. He's now at Stanford, I believe, doing his PhD. And Matthew Fluitt at Rochester, who has been instrumental in getting this project going and still quite involved as well. So let me jump in. So in the world of parallel programming, I think historically there's been sort of a divide. There's kind of two different approaches you might take to parallel programming. On one hand, you might say, I want complete control over my memory, over my allocations, and so that's the kind of more imperative side of parallel programming. Gives you lots of control, but it's also maybe manual memory management and all this, but it's also very easy to make a mistake. Race conditions are something that we deal with every day, and I think more and more as programmers out in the world are becoming familiar with parallelism and concurrency, they're having to learn about these issues, like race conditions and how to deal with them. Now, for decades, in functional programming languages, researchers have argued that these languages are much simpler and it's easier to write parallel programs in these languages, because in these languages, there's an emphasis on immutability. So generally, you're allocating data rather than modifying existing data. That's kind of at a low level, that's sort of what it looks like. And in these languages, we also have like automatic memory management, automatic GC, these sorts of techniques. And generally, you get some sort of determinism guarantees by default, and you kind of avoid race conditions just for free. Okay, but now the first question you might have is like, well, all those things sound great, but doesn't that make my code slow? GC historically has been a big problem for performance. I mean, I think there's been decades and decades of research on trying to solve this problem, and still people, I think, have trouble with GC interfering with performance. And that's only a bigger issue in the parallel world, which I'll talk about today. But at the end of the day, the problem that we're trying to, the question we're trying to answer here is whether or not parallel functional programming really can be fast and scalable. Okay. Now, why is this difficult? Well, as I said, this emphasis on immutability and this emphasis on automatic memory management, these languages tend to have a very high rate of memory allocation. Like I mentioned, you tend to allocate memory rather than editing memory in place. So there's a very heavy reliance on GC. Now, in the sequential world, the garbage collection story is very simple, and I would even call it, to some degree, solved. This problem has been somewhat solved, I think, in the sequential world. Really simple picture, you have some shared memory that you have a mutator. This is Dijkstra's terminology, I believe. The mutator and the collector, you can think of these as like two concurrent processes operating on the shared resource, which is the memory. But there's sort of only one mutator and one collector, and you can coordinate with them very easily. So it's not too difficult in the sequential world. Now, in the parallel world, the situation is much more challenging, because essentially we have a bunch more mutators that are all hungry for memory. And so all of these, so each one of these, you can think about these as the threads in your program, or you could think about these as the processors in your computer. right? So if I have a nice laptop here with 16 cores, you could have 16 mutators all going after the memory at the same time. And the existing techniques for garbage collection, kind of the prior work on garbage collection, they all sort of have the same flavor of just kind of throwing a bunch of collectors in there to try to counteract the mutators action. So if you have lots of mutators, they can all be allocating at the same time. Then you need lots of lots of parallel collection in order to counteract that and reclaim memory. This approach in general just is high contention. The memory really is a shared resource. It doesn't scale, and we'd like it to scale. So what we're asking in this research is there a better way of doing a principled, structured approach to parallel GC? Okay, so I'd like to start just by giving you a little example of what parallel functional programming looks like. I imagine many of you are familiar, but just in case any of you is not, here's a tiny example. Let's do like numerical integration where summing like Riemann sums, right? Summing rectangles. How might you program this in a functional programming language? Here's some pseudocode. This is not in any particular language, but just, here's an idea. You have a function integrate. Now it actually takes a function as argument. This is one of the features of functional programming, is that functions are first class values that you can pass around. It takes this range A to B, that's the range that we're integrating over, and it takes n, let's say that's the number of rectangles we want to use. So delta is the width of the rectangle, that's fine. This first interesting thing is the function tabulate. This is the build an array function, okay? So this says build an array of size n and use this function to compute each element of the array. So that's just calculating the height of the ith rectangle. Good, so this in parallel builds an array for us, okay? And then the second step is, let's just sum up that array, right? So this is saying do a reduce over the heights. Reduce is like a divide and conquer parallel reduction, okay? And we give it a function which tells how to combine elements. So in this case, we're just combining by addition. And so this is computing the sum of that array. There you go, we get numerical integration. So if you're curious about actual work and span bounds, this would be linear work and a logarithmic span for this parallel algorithm. Okay. Another small example, a merge sort. Really, really simple. Excluding the base case, let's just look at the parallel case. You start with some input x. We split the problem into left and right, L and R, so that we can do those two halves in parallel. So this is what we call a fork. So we say that initially we have, we're trying to solve the M sort problem. Well, we fork and we decompose the problem into two subproblems that we can do in parallel. Okay, and that's what this function par in the or this keyword par in my pseudocode means. It just says do these two things in parallel. Okay, and then after those have been sorted, we can merge them together. And this merge itself could be a parallel subroutine. I mean, you can imagine I could write some more code that actually implements merge. The parallel under the hood, right? So altogether, you can get nice work efficient bound to n log n work and some sort of polylogarithmic span for this code. Okay. So this should give you a sense for kind of at a high level the code that we're picturing here. To get a sense for this high rate of allocation that I mentioned, just note that, for example, the merge function, in order to be purely functional, okay, it's a function of its inputs and it produces some output. That output really has to be freshly allocated. That's kind of the only way you could implement that merge function in a functional setting, is by actually allocating a separate array for the output. Whereas if you were doing a careful implementation of a merge sort in, say, C++ or something, maybe you could pre-allocate all the memory that you needed and then go in there and just move the bits around. Okay. So we've seen this fork and join structure that I just diagrammed there at the bottom of the slide. In order to handle allocation efficiently in a parallel functional language, what we're going to do is give each task its own heap. So you can, these are these little gray rectangles that I'm drawing here. Whenever you fork you create fresh empty heaps for the new tasks that you created. And then when you synchronize or when you join those tasks back, you merge their heaps back up into the parent. So anything that the children allocate gets returned back up to the parent task when it completes. This lets us do allocation really efficiently in parallel, because when you do an allocation, you know that you have a dedicated heap for that allocation. Okay, good. So let me define now this disentanglement property. This is the study of this work, and this is something that we've observed organically, kind of in these nested parallel fork join parallel codes. Okay, and we'll get into later as to like why we're seeing it, up here. But let me just define it first. So throughout execution, the property that we want is that each task only uses a subset of the kind of all of the data that's been allocated. So specifically, we're going to say that each task is only allowed to use data in local or ancestor heaps. In my little picture here, I've created these little white squares. You can imagine those are our objects that we've allocated. Each one has been allocated by the corresponding task. So if we pick a task, it's only like, and the leaf tasks in a fork join program, by the way, are the active tasks. The internal tasks are suspended. So you fork into two and you kind of wait until both complete and then you continue, right? So if we look at a leaf, it's only allowed to use data along its root to leaf path, okay? And like another leaf, same thing. You look at its root to leaf path, and that's the only data that it's allowed to use if we're disentangled. That's the only data it's allowed to use, okay? Why do you care? Well, hint, hint, parallel GC, and I'm going to get to that. But at the moment, let's just focus on this disentanglement property and like, what is it? And, so the first question you might have is like, what sorts of programs actually are disentangled, right? It seems like kind of a restriction. I'm not allowed to allocate something and then hand it off to a sibling. Okay, so the first question we were trying to ask is what sorts of programs have this property? Okay. I put mutation free here just because, like, from a perspective of parallel functional programming, that's maybe like the world that you're in. It's the no mutation, right? But that's a very, very strict requirement. And you can imagine in that code that I showed you earlier for the merge sort, that merge function, let's say. Under the hood, I mean, maybe I, as an expert parallel programmer, supposedly expert parallel programmer, I could write a library that implements that merge for you. And maybe under the hood, I can use mutation and whatever I need in order to get the efficiency that I want. Okay, but now I'll provide you this nice black box merge function that you don't have to worry about all of those details, and you can just use it in a purely functional setting. If you're in that sort of setting, there is mutation in your system. So you're not mutation free like that. You can have mutation in your system, okay? But maybe what you're more so is like you're in a race-free setting, okay? Because maybe that merge I implemented as a race-free subroutine, okay? And now if I just compose race-free subroutines in a purely functional way, you get also a program which is race-free. And so, okay, what we notice is that these programs tend to be disentangled. That's kind of cool. And actually what we've discovered is that disentanglement is strictly more general than race-free. So if you can guarantee that a program is race-free, you actually get this disentanglement property. And that's something that we're really excited about, because as we will see later, we can take advantage of this for better memory management. Okay. So in our paper from 2020, this is at Provably 2020, we proved this property that all race-free programs are disentangled. Let me just mention that the notion of race here is the notion of a determinacy race. And what this means is that if you are free of determinacy races, your program is very strongly deterministic in the sense that even at the level of individual memory reads and writes, it does the same thing every time, no matter how you schedule it. So that's the kind of race freedom that I'm talking about here. It's a very strong deterministic kind of race freedom. Okay, so now why should race freedom imply disentanglement? Why is this the case? Here's some intuition. So suppose you had entanglement in a program. Now entanglement means like a thread is accessing data that was allocated concurrently by like some other thread. Okay. If that's the case, that thread that has this cross-reference to some other data, it must have read what we call a down pointer. So in illustration, here's what a down pointer looks like. We've got our little tree of heaps, and on the left, that task must have allocated a piece of memory and then stored a pointer to that piece of memory at some shared location up above. So that creates a pointer down to it, as we call it a down pointer. And now that down pointer must have been read concurrently by this other task. And now that red arrow there, that's the entanglement in the program. But in order to do this, I had to erase. I have to have a read-write race. I have to create the down pointer, and then I have to read the down pointer. And that constitutes a race. So that's the intuition for where disentanglement really, entanglement only emerges because of a race in your program. Now, kind of more directly, if we want to prove, so that's the intuition that like entanglement is only created by races. But now the actual proof that race freedom implies disentanglement is a bit more nuanced. We identified this single step invariant, which is really nice. It says that if it's okay for a thread to access a particular location, so let's say if it's okay for that thread to read, if it's okay for a thread to read from a particular location, then you have this kind of one hop property that anything that is pointing to is also in the root to leaf path. And so then you can kind of like carry this single step invariant through a race-free execution and see that you actually have this entanglement the whole time. Excellent. So we've seen that race freedom implies disentanglement. Now, a lot of parallel programs actually, it turns out, are race-free. That's part of the reason why we think disentanglement is really common. How common is disentanglement? Well, here's just a little sample. We looked at Ligra is some of Julian's work here today. PBBS also, the community here at MIT, I think has been heavily involved in developing this benchmark suite of parallel algorithms. And what we're finding is that all of these codes are disentangled. Now, partially that's because of race freedom, okay? But if you look under the hood, actually you see that there's lots of what we call like maybe benign races happening in these codes. What's a good example of this? It's kind of pervasive in Ligra because a good example of this is using like a compare and swap to do some on-the-fly synchronization between two threads that are concurrently running. So for example, in Ligra, two threads trying to visit the same vertex at the same time, you might do a compare and swap on a flag to claim access to that vertex in a graph search or something like that. And we've seen in PBBS, this sort of phenomenon is quite useful for a few benchmarks as well. So even despite these like uses of races, like this particular use case for races, we're seeing that these programs are still disentangled. I have a lot of speculation about why that is. Perhaps the way in which we manage our memory very carefully as parallel programmers kind of naturally leads to disentanglement. For example, one of the things we tend to do is we pre-allocate the memory that we need and then do a lot of parallel processing on that memory without needing to allocate fresh stuff. And that sort of paradigm is naturally disentangled in a very simple way. You put aside the memory before everybody goes and accesses it. So you don't have allocations happening in parallel and you get disentanglement. Anyway, this is something that I'd like to understand better. I think what we're seeing is that disentanglement is extremely common, even in high-performance high-performance parallel programs that have races. Okay. Good, so just reiterating, that's kind of where disentanglement sits. It's not fully general because of course there is some restriction in it, but it is more general than race freedom. Okay. So let's get back to the original question. We're trying to figure out, is there a better way of doing parallel memory management for parallel programs in general? I mean, as we've seen, disentanglement is not something which is strictly unique to parallel functional programming. It's actually, in this benchmark suite, PBBS, this is stuff written in C, C++. So even in these programs, we're seeing disentanglement. So is there, maybe there's a kind of a general idea here that we can capture. Is there a better way of doing parallel memory management? Okay. Well, this fork join discipline that I introduced earlier, we were talking about merge sort, for example. Decompose into two problems, you solve them in parallel, you join them back up. That gives you a tree structuring to your mutators, if you will. Like the mutators in your program have this tree structure. And disentanglement gives a tree structure to the memory that those mutators are accessing. So then we should be able to come up with a garbage collection policy that takes advantage of that tree structure to get better performance. Here's our approach to this. How do you take advantage of this tree structure? What we'd like to do is we'd like to assign heaps to processors. And the idea in the back of the head is we want each heap to manage its own memory, just the heaps that are assigned to it. Sorry, we want each processor to manage just the heaps that are assigned to it. Okay. So I'm going to draw some bubbles here. There you go. Let's say this is our heap assignment at this moment in our program. I'm drawing these bubbles kind of suggestively. I'm going to show you a technique for assigning heaps on the fly that kind of is going to give you something that looks like this. So you can see this forms a partition. So every heap is assigned to a processor. Okay. And the idea is that if a processor wanted to do a garbage collection, it would do it within its own bubble. Okay. So now what specifically is the strategy that we're going to use for assigning heaps to processors? Here's an idea. Let's integrate closely with the thread scheduler. So the thread scheduler that we're using in this case is like a work stealing scheduler. Perhaps you can generalize this for other schedulers as well. But let's talk about work stealing a little bit. So one of the simplest thing you might see is a fork in the program. What we're going to do in this case is okay, the scheduler is going to make, you fork into two things. The scheduler is going to make one of them available to be stolen. So it's going to put that onto a queue to make it available for some other processor to work on. And meanwhile, the other thing, it's going to start working on. And so what we can do is just go ahead and create a new heap for the stuff that processor is working on locally and assign that heap to the same processor. It makes sense. It's all local computation. It makes sense to put it in the same place. Okay. Now the counterpart to that fork would be like a steal, right? We made this thing available for somebody to steal it. And what that would look like is somebody coming in, taking that task, actually instantiating it as a real thread, okay, and starting to run it. That all happens on another processor, and we're going to assign that new heap for that new task on the other processor. So that's where we're kind of now seeing separation of bubbles that we're assigning. Okay. So this lets us create parallelism. Now, how about joining back in, synchronizing? Okay, so at a join point, what you have is two subtasks that one of them might complete before the other, but they're both trying to synchronize back into their parent. Okay. So here's one particular case. Let's suppose the left-hand side finished first. What we're going to do is what we call a surrender. And a surrender just says, take all of my heaps on the current processor and give them to the other processor. Right? So you're trying to synchronize with this sibling. And so you're just going to take all of your heaps and give them over to the other processor. There's kind of a symmetric case if going in the other direction. Like if the right-hand side finished first, then the color of the bubble would be blue. Like then the purple heaps would go all into the blue heaps. But so there's kind of two surrender cases here: left finishing first or right finishing first. Now, if you actually assign your heaps in this way, you get these nice bubbles like I drew earlier. You get these spines assigned to each processor. Okay. So great. Now we have heaps assigned to processors. Disjoint, it's like a partition of our heaps assigned to processors, right? And now we would like to be able to say, like, let's do garbage collections on these heaps. Let's suppose for a moment, I haven't explained yet how we actually do the garbage collection, but let's suppose that we're able to just pick a bubble and do a GC on it. And being able to do that relies on disentanglement, and we'll get to that in a moment. But for now, let's just suppose we have this magical ability to just do a GC on one of these bubbles. Now you're left with a question. When do you do a GC? I mean, you can't do it all the time. That would be too expensive. You can't just never do it. Obviously, you'll run out of memory. So you need to schedule like the moments that you decide to trigger a GC on these bubbles throughout the tree of heaps. Okay. So here's a simple algorithm for you. We're going to give each processor just a local count, call it LP. And L stands for like live. So think about this like a live memory notion here. Okay. You can set that counter to some initial small constant, doesn't really matter. You can even set it to 0, it still works. So what you're going to do on each processor, this is entirely local on the processor. You're not like looking at anybody else's heaps. You're going to wait until your bubble gets too big. So when your bubble exceeds k times LP, so k is just some amortization constant, maybe 2, 4, 8, something like that. You can pick any constant, doesn't matter. When the size of your bubble gets too big, that's now when you're going to perform a GC on your bubble. Okay, you perform that GC, that's going to reclaim some memory. So some memory is going to disappear, some memory is going to survive. And what you're going to do now is set your counter, L, to the amount of memory that survives. Very, very simple collection policy here. And completely distributed, like each processor only needs to look at its own memory in order to do this GC decision. Okay, so now, how does it perform? This is from our recent POPL paper in POPL 2021. And the Aurora here, that's Jatin, he's here today in the audience as well. So this is the result that we worked on together. This says that if you have a race-free program, and let's suppose that the amount of work, the total amount of work that that program does is W, and let R star be the sequential memory footprint of that program. I'm going to get back to this R star thing. Let's just intuitively think about it as memory footprints for the sequential execution. Now, if we do parallel execution on P processors, then we need P times R star space, and we need W plus P times R star total amount of work. And that includes the cost of garbage collection. So what we're picturing here is you pick a bubble, you do GC on it, that costs like the size of the bubble. You have to pay for the size of the bubble in order to do GC, okay? So that's included in the work costs that you're seeing here in the theorem. And the space is also measuring like the cost of GC. But really what you're seeing is the fact that a lot of these bubbles can exist at the same time. So if you imagine that like each bubble is sort of like R star and you have as many as P of them, then you get P times R star space. Okay. But now that intuition that each bubble should be like R star, like let's dig into that a little bit. Okay. What's the key idea here? These bubbles really do resemble sequential executions. What I mean by that is that the live memory within a bubble is sort of like a subset of the live memory that existed at a certain moment in a sequential execution. Okay. Now, typical sequential execution, when you think about sequentially executing a parallel program, what do you do at a fork? The kind of most obvious thing would be, okay, I fork two things. I'll do the left side first to completion, and then I'll do the right side to completion, and that's how I'll do a fork. That's how I'll sequentially execute a parallel fork. That's one possible sequential schedule, but there's another very reasonable sequential schedule you could do, which is to do right before left, rather than left before right. And this is where the nuance of this definition R star comes in. R star says, allow for either one. So you're kind of looking at all possible sequential schedules. Okay. Some of them are going to do, do the left and then the right, others are going to do the right and then the left, and you're going to have all a mixture of these. And the key idea is that after you surrender your memory, so when you're done working on a task and you surrender your memory off to another processor, there's kind of two cases. Did the left finish before the right, or did the right finish before the left? If the left finished before the right, well, then the new bubble kind of just looks like the normal left before right sequential execution. But if the right finished before the left, that's when the new bubble kind of looks like doing the right-hand side before the left-hand side. That's kind of the intuition behind this proof. And then the last thing just to notice here is that there's sort of a key lemma that we prove in the paper, which is that these local counters can't exceed R star. And so that's where you get this P times R star then come in, because the sort of the size of each bubble is sort of like R star. And then you can have as many bubbles. That's kind of the intuition. It's not exactly all the details, but I'll let you look at the paper if you're curious about more details there. Let me just mention a few things here. So this P times R star, that might seem like a big inflation of memory. Like if I'm using 100 cores, am I using 100 times more memory? So actually, the interesting thing here is that this is a fundamental consequence of parallel execution, that some programs require more memory in order to run in parallel. Okay. So this factor P increase in the amount of memory you're using for some parallel programs is actually just fundamental. So if we got a bounds that was lower than P times R, that would be very suspect, because that would suggest that maybe we're reducing parallelism in order to use less space. Okay. And then this increase in the work term. Well, let me at least say that in our experiments, we're not really seeing a massive overhead to these techniques. So there's probably something loose here. And the intuition here is just that, okay, if you're using as much as P times R star memory, well, then it has to show up in the work term somehow, because you have to pay for allocating it and you have to pay for collecting it. Okay. So we find these bounds pretty promising, I think is what we're saying here. The last thing I want to say, this R star thing. We're looking at all sequential schedules, right? Seems a little iffy, but let me just mention that we're looking at sort of maximum memory footprint over all sequential schedules. You could also be curious about what's the minimum footprint over all sequential schedules, right? And is there really a gap between the two? And so that's something that I'm kind of curious about looking into in the future. It feels to me like that gap for typical well parallelized parallel programs, it feels to me like that gap is not very huge. So, okay, so there we go. There's our algorithm. So now how do you actually do GC? Now we get to come back to disentanglement. Okay. We have these bubbles, right? Coming back to this in our little picture. We have these bubbles and we want to be able to do GC on a bubble independently without talking to other processors, without communicating, without synchronizing. Okay. So how do we do that? Well, disentanglement provides us this really nice property, that there's no cross pointers in our tree of heaps. So every pointer then is either pointing up or down. Like we saw earlier, that down pointer that we were talking about for the race freedom that implies disentanglement proof. So that's what we mean by a down pointer, and then up pointer would be pointing in the opposite direction. Right? You also have these internal pointers, within one heap, but let's just call those up pointers just for the sake of simplicity. Okay. So now the roots for GC kind of live at the leaves. The leaves of your tree of heaps, that's where the active tasks are. And if you go look at those tasks, each one of those tasks has a program stack. You go look through the program stack, you figure out, what is it currently using? That's how you can get a sense for the GC roots. Let's just think of those as up pointers, right? So now we've kind of reduced this problem into just saying how do we handle up pointers and down pointers? These are the two things we have to do. So let's look at a bubble. So this is one bubble assigned to a processor, let's say. So there's some stuff above it. There's some ancestor heaps that are assigned to some other processor, okay? There's potentially some stuff below it. These are stolen tasks that are assigned to a local processor, okay? And then there's some heap down at the bottom, some leaf heap, which is the active task on this processor. Okay, so how do we handle down pointers? These are pointers from these ancestor heaps down into our local bubble. This is actually really standard in other GC literature. For example, generational garbage collectors need to remember these intergenerational pointers. And it's a very analogous situation here. We have these down pointers, and what we can do is use a write barrier. So a write barrier is just a small snippet of code that runs when you mutate memory. When you mutate memory. So this is inserted by the compiler. The compiler inserts these little write barriers, okay? And the write barrier is going to do something like test to see if the pointer you're creating points down, and if so, write it down somewhere. So we have this little remembered set that's kind of sitting off to the side, which is these down pointers. Okay. So that handles the down pointers for us. But what about the up pointers? So these are the pointers coming up from tasks that were stolen. And this is where we introduce a new idea, this we call snapshotting at fork. So what we're going to do, imagine you have a task, it's about to fork. Recall that the scheduler, what it does is it puts one task on the deck, on the queue for work stealing, and then it starts working on the other side. That thing that it puts on the queue, it's a closure object, which describes the task. So it's describing how to execute the task. Here's a really cool observation. Everything the task needs in that heap is given to us by that closure. Look at that closure, look at the memory reachable from that closure. Those are the objects that that task might need access to. Right? So what we do is just put that, we call that a snapshot. This is the process of snapshotting. It's like, take a picture of the heap, kind of at the fork. All you have to do though is store like this single object, essentially. You store this right side closure as an additional root, if you will, for this heap. And note that this doesn't violate this R star bound that we had earlier. Remember that we don't want to preserve too much memory inside of these bubbles. The closure is a safe approximation because everything that would be needed by that task is live while you're executing the left-hand side anyway. Like you have to keep that stuff around until you can actually run the other task. So it's actually safe to store this closure and say, like, just keep everything alive with this closure that's reachable from this moment. We actually use, so part of snapshotting then is preserving that reachability. So you're saying that this stuff is reachable from this object, okay? And I want to make sure that I keep all that stuff alive. Well, people can be coming in and editing memory kind of concurrently. Like one of the descendants could come in and swing a pointer somewhere else. So we're also using the right barrier here to make sure that when we swing a pointer away from something, we keep track of that object. Just so that we don't accidentally kind of lose the snapshot. We don't want to lose the snapshot. Good. This gives us some idea for how to take advantage of disentanglement in order to do garbage collection. But let me just go a little bit further and mention that essentially now we have two different forms of GC in our system. We have one that we call an internal collection and another one which we call a local collection. The internal collections are the ones that need to use the snapshots. And these have, they kind of fundamentally have to be concurrent algorithms. You have to use a concurrent GC algorithm in order to do an internal collection because there might be concurrent accesses from your descendants that are accessing that heap. Sorry, there's somebody mowing in my background. Now, the other kind of collection would be what we call a local collection. So these are in the kind of down near the leaves. These are heaps that only have one child. And so you know that there's only one task accessing those heaps. And so then you can do like even a sequential GC algorithm, and you can do it like any algorithm you want. The one that we implement in our system is a compactifying, like a copying collection, like a Cheney style collection. Whereas for the internal collections, we do a non-moving mark sweep, which is safe for concurrency. Good. So there we go. There's the theory of disentanglement, how to do GC, how to do parallel GC, how to do it in a provably efficient way. We've been implementing this in a compiler called MPL, or Maple, as we pronounce it. It's based on Milton, and it's a compiler for standard ML. So standard ML is this functional language. We use it at Carnegie Mellon quite a lot for even pedagogy in undergraduate courses. Okay. It's a very simple functional language. If you are familiar with OCaml, if you've heard of OCaml, it's very similar to OCaml. OCaml kind of has more features than standard ML. But standard ML is this nice kind of simple. It actually has a formal proof of correctness too, which is one cool thing about it. So what we did, so Milton is I think the fastest compiler for standard ML that exists today, and actually probably is the fastest compiler for any functional programming language that exists, at least for sequential code. It's really impressive how fast it is, like often within like a factor 2 of C code for like kind of similar kind of programs. So what we did is we extended it with this par function. We saw that in my pseudocode earlier. It's basically just saying if you have two functions, you can execute them in parallel. Okay, so in the ML type system, that's just saying that tick A, that's just saying like something, you have this type like A, you have some type B, you can say like, okay, run two functions, one that produces an A, one that produces a B, and I'll give you back a tuple of the results. Good, so as I mentioned, we're using this at CMU to help teach parallel programming. There's an undergraduate course called 15210. This is developed by my advisor, Umut Takar, and also Guy Block. Those two kind of have co-developed this course together. It teaches parallel programming using standard ML. And nowadays we're using Maple in that class to let the students actually run their programs and see real performance improvements, real speed ups. So yeah, speaking of performance, let's talk about performance. How good is Maple doing after we've implemented all of this stuff that I've just talked about, all of this GC stuff? First thing I'd like to look at is a little sorting shootout competition, little sorting competition. So we collected some of the fastest parallel sorts that we could find. So in Silk, these are algorithms in the PBBS benchmark suite. So there's two different algorithms here, a sample sort and a merge sort. We got Maple there, we implemented a merge sort. And then a few other things. So how about Go? Java, the implementation in Java is by Doug Lee. Doug Lee is one of the core developers really for Java, I guess is one way of describing it. But he implemented all of the parallelism and concurrency stuff, like the Java fork join framework, which like parallel streams is based on and all that stuff. So anyway, this is Doug Lee's merge sort that we're running. And we also found in Haskell, we found a merge sort that's kind of this hybrid thing. It also calls out to C to do some of the subroutines and stuff. But anyway, fastest parallel sorts that we can find. And what we're seeing is that the Maple is actually the fastest out of the ones that have automatic memory management. So Maple, Go, Java, Haskell, all those have automatic memory management, automatic GC. And out of these, Maple is easily the winner. You might notice that the times on one core, so the T1 is on one core, T72 is on 72 cores. The times on one core are kind of all over the place. Right? So for example, Maple has factor 2 overhead over C, like the C standard sort or the Silk sample sort. So we're seeing like a factor 2 overhead there. And yet, down at T72, we're still seeing a 24x speed up over the C++ standard sort. So this is quite fast that we're able to get. And like I said, we're on 72 cores, we're something like 40% faster than the sort in Go and 70% faster than Go. So some speedups for you also. So these are on PBBS style benchmarks. So these are benchmarks that were either kind of inspired by or directly ported from this problem-based benchmark suite, which has been developed by quite a few folks here at MIT as well as at other institutions. And as far as we know, these are some of the fastest kind of fork join multi-core parallel codes that you can find. And what we're seeing is great speedups with Maple. Now this is in comparison to Milton for a fair comparison. If you wanted to compare against C, you kind of, chop them in half. That's kind of approximately what I would say you want to do. We're seeing in general like a factor 2 to 3 overhead in comparison to C, kind of across the board. But for a parallel functional language, a factor 2 overhead over C, I think that's very acceptable considering how much easier it is to write parallel programs in this stuff. So how about space overheads? This is the last piece of this discussion we're missing, I think. How much more memory do you need in order to actually do parallel execution? Right. Our theory earlier said you could need up to a factor P more, but that's really pessimistic actually. Typical parallel programs don't need that much more memory in order to do parallel execution. And on our benchmarks here, what we're seeing is actually that typically less than 5 factor space blowup is common. So once again, this is relative to Milton. So we're taking the maximum resident space of Milton when you run it on this program. And then we run it with Maple in parallel, and we look at how much more resident memory that you need in order to execute it. And we're seeing, typically, less than say 5x to do 70 processors. Okay. I want to point out a lot of the memory overheads actually here are lower than 1. So there are multiple places where we're using less memory than Milton. And just the intuition here is that, okay, you're in parallel, like we're running in parallel, we're getting potentially factor 10, 20, 30x speed up, and we're using less memory. Like, how is that possible? The intuition here is that like sequential GC policies typically have kind of a large slack in the amount of memory you're allowed to use before you trigger a GC. And Maple is a bit more aggressive with GC because it's doing GC in parallel. It's kind of doing more GC than Milton will be doing, and potentially reclaiming the memory faster. So that's just kind of the intuition. So in conclusion, I think what we're seeing here is really good performance out of this thing. It's pretty stable. It's being used by, like I said, hundreds of students at CMU, so we're getting lots of testing by doing it that way, and really good performance. So I think all of this, all this overhead of managing this tree of heaps and triggering these GCs, it's actually turning out to be quite reasonable and quite practical. So that's about it. Thank you for your attention, and please go download Maple and play with it, and we'd love to hear your feedback. So thank you.
Great. Thanks a lot, Sam, for the talk. Yeah, so if anyone has any questions, please feel free to speak up or type in the chat. Yeah, so I'll start off with a question. So I'm curious what happens if like you take a program that's not disentangled and run it in your system. Is it going to be incorrect or just going to be slower?
So at the moment, it's just incorrect in our system.
I see.
Which is unfortunate, but this is something we're working on. Like there's kind of 2 different approaches you could use to solve that. You could do like a static analysis approach, like maybe a type system or something like this, that could enforce disentanglement. The other thing we're kind of looking into is this idea of detecting entanglement kind of on the fly, sort of like race detection. You could detect entanglement on the fly. And we're working on this, and we have reason to believe that actually the overheads of doing this could be like surprisingly low. So that seems to be a pretty promising approach to just kind of, you run your program and you just like check to see like, is there entanglement? And possibly then even you could integrate this with the memory management system. If you can detect entanglement cheaply on the fly, then maybe you can just run it with entanglement detection always turned on. And when you detect it, you gracefully recover from it somehow. So that would give us like a fully safe version of it. But yeah, at the moment it's technically unsafe. Yeah.
Okay, thanks. And a related question is, do you have any like general techniques for making a program disentangled if it was originally entangled?
Oh, good. So like taking an entangled program and making it disentangled.
Yeah.
Let me just say first, before I get into that, that actually guaranteeing that a program is disentangled is not too hard, particularly in a functional programming language. Because, for example, in this undergraduate course, 15.210, we give students this nice parallel library. It has parallel merge, it has tabulate, it has reduce, it has these sorts of things in it. We implement the library, and then the students just go and they compose these functions in that space. So the students are writing purely functional code. If you write in this style, you get disentanglement for free. Like nothing you have to worry about, right? So that's one thing. So like if you want to make your program, disentangled, that's one kind of approach you could do. You could kind of like migrate it to a more functional style, I guess is one. Yeah. But in my experience, like porting PBS benchmarks and trying to guarantee that they're disentangled and this sort of thing, I actually find it's not too difficult. This idea of pre-allocating memory and then manipulating it is really powerful. Like you can get really, really far with that idea. And so, for example, I think, how about parallel Kruskal's, parallel Kruskal, like MST, benchmark. If you're doing concurrent union find, if you pre-allocate all your nodes, this becomes really easy. And actually, then you're probably using pre-allocate all the nodes in the union find tree. It becomes really easy to like manipulate the memory. It becomes more compact because you just allocate an array of like integers or something to do union find. Right? So like these sorts of ideas tend to lead towards disentanglement. And I find they tend to improve the performance of the parallel code anyway.
I see.
So, but that's
that
sort of idea is kind of pure speculation at the moment. Like, does writing in a disentangled style get you better parallel performance? Well, it gets you better GC, like I showed you here, but like, does it really make the algorithm better? That's kind of unclear. We're not sure yet.
Yeah, we found that to improve performance because, I mean, there, like with the default memory allocator, there's contention on it if you do a bunch of allocations in parallel. So in our PVBS benchmarks, we tried to do everything. Like, I guess we tried to pre-allocate all the memory if possible.
Yeah. And I think that style, leads to this, which is pretty cool.
Yeah, great, thanks. There's a question from Artem in the chat. So the question is, does it play well with generational GC, and do you plan to have it in your implementation?
It's a great question. So for those of you who aren't familiar, generational GC is this strategy of doing GC where if an object survives a lot of collections, or maybe even one, if an object survives collection, you kind of put it in a separate place and you don't collect it as often. So I just want to mention, actually, in our design, there's sort of a natural kind of generational flavor to the tree of heaps, because the heaps that are down near the bottom potentially are collected more frequently, or could be collected more frequently, if you'd like them to be, than the heaps that are up at the top. And for example, at the root, that's kind of where all the old memory collects. It's like at the root. So there's kind of already a natural generational kind of flavor to this design. But that being said, we have also considered, like, is there a way of doing kind of a more traditional generational idea in this design? I think one potential possibility you could do is you can imagine like two trees. Like we have one tree, but you can imagine like two trees that kind of overlap. And you can have the old generation and the old tree and a new generation and the new tree. And then they would move in tandem. They would fork and join in tandem, something like this. It could be a really powerful technique. Yeah, that's a really cool idea.
Great, thanks. Are there any other questions? Okay, yeah, it seems like there are no additional questions right now. Yeah, so if anyone thinks of any other questions, I guess you can contact Sam or send me an email and I'll forward it over to Sam. Yeah, and the GitHub link is on this slide if you want to check it out. Great, and yeah, let's thank Sam again for the talk.
Thank you. Yeah, thank you for inviting me, Julian. I really enjoyed it.
Yeah, it was very, very interesting talk, and I was very happy to learn more about the work that you're doing. Yeah. And if you don't mind, would you be able to send me your slides so I could post it on the website?
Is PDF easiest? Is that?
Yeah, that would be good. Yeah.
Great. I can do that.
Yeah. Great. All right. Well, thanks again, and take care.
Great. Thank you. Yeah, and thank you everybody for coming today.